Okay, so I've been asked by a couple of people about this idea of how to define continuity and how to solve problems involving continuity and differentiability. So I've decided to do a quick review and then we'll take a look at a problem. First thing to remember is that for a function to be continuous at a point where x equals a, the definition says that the left limit has to equal the right limit has to equal the function. In other words, the limit as x approaches a from the left of the function has to equal the limit as x approaches a from the right of the function has to equal f at a. Differentiability requires a little bit more. It requires all of that. It requires that the function is in fact continuous, and it also requires that the left slope has to equal right slope, which means that we need to meet the condition for continuity that we just said above. We also need to meet the condition that the limit as x approaches a from the left of f prime at x has to equal the limit as x approaches a from the right of f prime at x. One very important thing to remember is that you cannot solve a problem involving continuity without using limits. If you try, you're going to lose a lot of points, even if you get the right answers, which you very well might. So let's take a look at this example. We've got this function, which is a piecewise defined function, and we see that one of the pieces involves the absolute value. We're asked to express the function without using the absolute value symbol, and then to describe all values of a and m for which the function is continuous, and then ask for what values of a and m is the function going to be differentiable. Part A is generally not asked in the question, but part A would be required even if it wasn't asked. You can't work with an absolute value function if you're trying to do algebra. If you're trying to take a derivative or trying to take an antiderivative, you can't do that with an absolute value function. So anytime you've got an absolute value function and you want to do any kind of algebraic operations on it, you have to turn that into a piecewise function. So the first thing we're going to do here is we're going to try and take this function here and turn it into a piecewise defined function. The way we do that is we look at this part. Okay, this part is called the argument. And all that absolute value does is it says if the argument, if the thing inside the absolute value bars is negative, it multiplies by -1. And if the thing inside the absolute value bars, if the argument is positive, then it doesn't do anything, or it multiplies by 1. And so what we really need to do in these types of questions is figure out where is the argument going to equal 0 and where is the argument going to fail to exist. Because in order to switch from negative to positive, it either has to go through 0 or jump across the axis, which means that the function would not exist. This is a quadratic inside the argument, so we can see it's going to exist everywhere. So really what we want to know is where is x minus 4 squared minus 4 going to equal 0? And that's pretty straightforward. We can solve that quite quickly. We'll get x minus 4 squared equals 4. X minus 4 equals plus or minus 2. Don't forget that when we go from a quadratic function to a linear function, we're going to have two answers. So x equals 4 plus 2, which is 6, or x equals 4 minus 2, which is 2. So those are our possibilities. And now we can rewrite this function piecewise. So the function we had originally was a times the absolute value of x minus 4 squared minus 4. And we can now break this up into 3 pieces. We're going to have the piece where x is greater than or equal to 6. We're going to have a piece from 2 to 6. And we're going to have a piece where x is less than or equal to 2. When x is greater than 6, we imagine putting a number in here. If we put in a 10, we're going to get 10 minus 4 is 6 squared is 36, minus 4 is 32. That's a positive. So if this is positive, then the absolute value bars don't really do anything to it. And so this is just going to become a times x minus 4 squared minus 4. If we take a number between 2 and 6, say 4, if I put a 4 in here, I get 4 minus 4 is 0. 0 squared is 0 minus 4. We see we have a negative in here. And what the absolute value bars will do is multiply that by -1. So now I'm going to get negative a times x minus 4 squared minus 4. Okay, and that negative is going to multiply through this entire thing. A better way of doing that would be to say, let's take the negative inside, and this will just become a positive, and this will become a negative. So it would have been a little bit nicer had we written this like this. Positive a times 4 minus x minus 4 squared. That's the same thing, it's just a little bit cleaner. In the bottom, we have a number less than 2, so let's call it 0. If I put a 0 in here, I get 0 minus 4 is 4, squared is 16, minus 4 is a positive, and if it's positive, then the absolute value bars don't change it, and so we have the same thing as we had on the top, x minus 4 squared here, minus 4. So those are the three pieces we have. Now if I go back up to my original function, I see that this only applies to x greater than or equal to 3. And so that tells me that x less than or equal to 2 is not really going to be necessary anymore. Okay, we're not going to use that part. So all of this we can ignore. It also tells me that from 2 to 6, what I'm really interested in is from 3 to 6, because this function only actually begins at 3. For less than 3, we've got this bottom function. So now I can rewrite f at x the way that it should be. And so f at x is going to be the piecewise defined function. At the top, it's what we have up here. So a times x minus 4 squared minus 4 when x is greater than or equal to 6. In the middle, we're going to have what we had up at the top, a times 4 minus x minus 4 squared, and that's going now from 3 to 6. And at the bottom, we're going to have the function that we had at the top, mx minus 6, when x is less than 3. So that's what f at x is going to look like without the absolute values. And now that we know that, we can start to solve the continuity. So what I'm going to do is I'm going to copy just this function, and I'm going to take it with me to the next page. So this is the function we're dealing with, and what we want to do now is test to see whether this function is continuous and whether it's differentiable. So we begin by looking at continuity. Remember, for continuity, what do we need? Well, we're interested in whether it's continuous at 3. So for continuity at x equals 3, we need limit as x approaches 3 from the left of the function to equal limit as x approaches 3 from the right of the function to equal f at 3. That's what we're trying to find out. So let's take a look and see if that's true. The limit as x approaches 3 from the left of the function is really the limit as x approaches 3 from the left. And if I'm coming from the left, I can see that I'm on this piece of the function to the left of 3. So this is going to be the limit as x approaches 3 from the left of mx minus 6, and that's going to give us 3m minus 6. So there's my left limit. Now I need to do the same thing for the right limit. So I want to see what is the limit as x approaches 3 from the right of f at x, and that's going to equal the limit as x approaches 3 from the right of which function? Well, as I'm approaching 3 from numbers bigger than 3, I can see I'm going to be on this piece, okay, a little to the right of 3. So that's going to give me here a times 4 minus x squared. And if I put in a 3 here, 4 minus 3 is 1, 1 squared is 1, 4 minus 1 is 3. So this is just going to come out to be 3a. And that's also going to be equal to f at 3. And so for continuity, what I need is for 3m minus 6, in other words, the left limit, to equal 3a, in other words, the right limit. And I can clean this up a little bit, and I'm going to see if I divide a 3 all the way through, I get m minus 2 equals a. And finally, I can express this as m equals a plus 2. The original question asked us for the conditions such that the function would be continuous at x equals 3. And what we find is that we've got this condition, m equals a plus 2, which means there's an infinite number of possibilities as long as m is 2 bigger than a. So for example, if a equals 0 and m equals 2, that would work. If a equals 6, m equals 8, that would work. There's an infinite number of answers, and all we have to do is describe them, and that's what we've done here. Now we can move on to the last part of the question, which is asking us about differentiability. In order for the function to be differentiable, I need two things. One, I need it to be continuous, which I've already done. That's up here. So I still need m equals a plus 2. I also need that it's continuous, that its left slope equals the right slope. So what I'm going to say here is for differentiability, I need continuity, which we've already established in the previous part, and I need left slope to equal right slope. Like I say, I've already done the first part. I've already got the continuity, so I'm going to focus on left slope equals right slope. In order to do that, I need to know the derivative. And this is why we had to break that function apart earlier. Because in order to get the derivative, I'm going to take the derivative up here. I couldn't take the derivative if I had the absolute values. But now, this is fairly straightforward to take the derivative of. So my derivative is going to be, well, the top part is just going to come out to be 2a times x minus 4 when x is greater than 6. And let's just go up and see if we can figure out why that is. We see here, a is just a constant, so I take the derivative of this. I've got 2 times x minus 4 to the first power. The d box is just going to give me a 1. The derivative of 4 is 0, so I end up with 2 times x minus 4 times a, which is what we have here. The other ones differentiate similarly. Here I'm going to get negative 2a times x minus 4 for 3 to 6. And the bottom one is just going to have a slope of m, and that's when x is less than 3. Notice I have not included any equal signs in here because I don't know if the derivative exists at these endpoints, because I don't know if it's going to line up yet. So I have to be a little more careful with that. What I want to know is it differentiable at 3? So I need the limit as x approaches 3 from the left of f prime at x to equal the limit as x approaches 3 from the right of f prime at x. The limit as x approaches 3 from the left of f prime at x is really the limit as x approaches 3 from the left, and I'm going to be from the left on this bottom function. So this is just m, and so of course the limit as x approaches 3 from the left of m, is m. Now I need the limit as x approaches 3 from the right of f prime at x, and that's going to be the limit as x approaches 3 from the right of 3 from the right is going to be this function. So I have my negative 2a times x minus 4. And if I put in a 3, 3 minus 4 is negative 1 times negative 2a gives me 2a. And so now I have that for differentiability, I need 2a to equal m. But previously, for continuity, I said that m had to equal a plus 2. If I solve those two equations simultaneously, I can substitute a plus 2 in for m, and I get 2a equals a plus 2. Subtracting the a over, I'm left with a equals 2. And I know that m equals 2a and a equals 2. So therefore, m equals 4. And so I'm finished now, and I can say that for this function to be differentiable, I need a equals 2 and m equals 4 to make the function differentiable. And that's all we do. Very important to remember that solving a problem like this, you must be doing everything in terms of limits. Other than that, they all kind of come out the same way. I hope this helped.